representable by circuits of logarithmic depth and polynomial size, as MC1, is equal to the class functions computable by branching programs of constant width and polynomial size. I'll describe in more detail the structure of branching programs generated by the Barrington's method. It turns out that with 5 k of these okay polynomial n can compute exactly those functions in MC1. So now maybe some definitions. We call the branching program, and now let S be a sequence of variables. Finite sequence. Now we call the branching program an S oblivious. If the sequence of node labels on each path from the source node to the sink is a subsequence of S. And now a KOBD is an S oblivious branching program where S is just the concatenation of K copies of for some permutation phi. So we get the K copies, concatenate them, get the sequence of variables, and that defines the sequence of variable testing for KOBD. So on any path from the source to the sink, we get the subsequence of this S.
But you can write also P without the power super index, just P of 1, right?
Because P transforms 1 into some index, and we should. That is, we test the variable whose index P transforms into 1. P transforms some index into the first one, and we should test this variable test. This is why we use the power minus 1.
And why can't we substitute and denote phi minus 1?
Yeah, we could. Anyway, the proof will exploit the notion of permutation branching program, a PBP. A permutation branching program of width K and length L will be given by the sequence of L instructions of this type. Where x, j sub I is some variable, and g, I, and h I are some permutations of order k. This instruction generates permutation sigma I postscript, which is gi if is 0 and hy otherwise. The whole permutational branching program computes composition sigma of x Now, we say that PVP computes some Boolean function f via some permutation tau, which is not the identity permutation. If And it can be shown that for an arbitrary PVP of width k and the length L, we can construct a usual branching program of width k and length k times L, computing the same function. I don't know whether I should show it or not. It's rather easy for those who are familiar with branching programs.
But there are only a few of them here.
That's why I'm asking. Should I? Okay, let's keep it.
Can you give us a definition of a branching program?
A branching program?
Yeah.
A branching program is a directed acyclic graph consisting of a designated source node, an inner node. A source node is also considered to be an inner node. Each of them of fan and fan out 2. One ledge gets the label 0, another gets the label 1. What's more, each inner node gets a label of some Boolean constant, Boolean variable, and we'll have sink nodes, usually 2, labeled by Boolean constants, without outgoing edges. Upon input, the computation upon input A starts from the source node. If the node is labeled by xi, we continue the process to the edge labeled by ai. And the computation finishes when we reach the sink node. So we say that the branching program computes a Boolean function f if for any such input the computation starting at the source node ends at the sink labeled f of a. That's it. Now, Barrington proved that given a circuit of depth d, we can construct a PBP of width 5, circuit of depth d, can construct a PBP of width 5, and length 4 to the d, to the power d. That is proved by induction. I can give you the sketch of the proof of the induction step. The circuit computes a function of the basis conjunction and negation. Negation is quite a simple operation for branching programs. We can construct the branching program for the negation of the function without changing the size and merely changing the last nodes. So we can consider the conjunction. Let our function f be computed as the conjunction of two sub-functions. By the induction hypothesis, we can construct two PVPs of length 4 delta to the d minus 1. Now, they are computing a function f2 via some permutations ρ1 and ρ2 respectively. There is a way for transforming those PVPs into PVPs computing the same function via another permutations r1 and r2, such that the commutator this permutation do not commute. we can as well convert these PPPs into another PPPs using these two permutations. And then we combine these 4 generated PPPs into one. Consequently, writing the instructions, we get the bigger one of length 4 to the d, and it's easy to show their computing function f. Because if one of the arguments is 0, it means that in this proposition, one of the tau 1 or tau 2 has tau 1 minus 1, and tau 2 to the minus 1 is equal to identity.